So let me introduce our first speaker, Stephen Malina, who is a machine learning scientist and team lead of the machine-guided design team at Dino Therapeutics, where he's focused on machine-guided design of He has a bachelor's in CS from Dartmouth and an MS from Columbia, and has worked at Uber learning models learn about epigenomics, and he's now focused on ML-guided protein design. So without further ado, Stephen, you can start sharing your slides and take it away.
Awesome. Can you see this okay? And hear me? Awesome. Okay, great. Well, yeah, thanks for having me. As Eli mentioned, I'm going to be presenting today on work we did about forecasting labels under distribution shift for machine-guided sequence design. This was work led by Lauren Wheelock, who unfortunately is sick today, so can't be here, and also worked on by myself, Chuck Gerald, Sam Sinai, and all of us work at Dino Therapeutics. And there's a link to our paper, which is on archive here as well. Okay, this is my conflict slide. So historically, biological sequence design, which again is what we're going to be talking about today, has had two paradigms. On the high library side, lower average quality side, we have random mutagenesis, which produces very large sequence libraries that we can measure, but most elements tend to be non-functional because we don't have anything guiding the mutation. They're just randomly chosen. And then on the other end of the spectrum here, we have rational design, which is using biological and other priors to design highly functional on a pure sequence per sequence basis libraries, but can be hard to scale for efficient exploration of sequence space, especially as we go farther from whatever our starting point is. And then there's this third paradigm, which is both what we're focused on at Dino, but also something a lot of people here work on in some form or another, which we call machine-guided design. And machine-guided design is just using machine learning models to design libraries that both have a large number of high-performing sequences, but also have high diversity and potentially can explore further out in sequence space. And again, hopefully this idea is familiar to many of you already. So a common sequence design scenario we often find ourselves in is we've used some sort of machine-guided design strategy or strategies to design a sequence library. And the sequence library, in our case, consists of viral proteins, but it could be any protein. It could be DNA sequences, promoters, RNA sequences, et cetera. And we're going to assay this experiment in the lab and get back a set of one or more measurements per sequence. And I should add that, we're typically assuming this is in the high throughput scenario, so we could have hundreds of thousands of sequences that we've designed individually. And this picture looks quite tidy. I think it looks quite nice, but it sort of hides that there's a problem that we often face when doing this type of design that I think is less common in other areas of machine learning, which is that these feedback loops can be really slow. So in our case at Dino, we do a lot of in vivo design, and the process of going all the way through the in vivo loop till we get back high quality data can take between 6 to 12 months sometimes. And so this presents a challenge where we'd really like to have some sense of how well our library will perform before we wait these 6 to 12 months and get it back. And so this is the problem we're going to be talking about today and proposing a solution to, where we want to have a forecast of how well our library will perform in aggregate that we don't need to wait for the experiment to come back from, and characterizes both the overall performance of the library, predicted performance of the library, and in particular, how well we expect top performers in the library to do, since if we're doing this design, we're trying to design good things, typically. So these forecasts serve different purposes at different stages of the experimental design loop. Before we've done the experiment, maybe after we've done the initial computational design, but we haven't finalized it yet, it can serve as a sanity check for sequence design. So if we typically have some sort of like qualitative or even quantitative sense of how well we think the design should be doing. And if the forecast is really out of sync with that, that suggests that our expectations may be wrong. We need to redesign or at least do some sort of investigation of what's going on. During the experiment, we can use forecasts to set and communicate expectations with people in the wet lab, other stakeholders, et cetera, depending on what situation you're in. And then after, we can get the data back and use that to improve our forecasting method. So the overall framework we're going to be talking about today is we assume that we start with some historical experiment data. So that could be a previous design. It could either be designed in a simpler way or a machine-guided design. And this gives us a set of sequences and associated measurements. We're going to assume that these measurements have a distribution, which we don't know the parametric form or whatever, they just have some distribution. And we're also going to assume that we use these measurements to train a machine model, which will also assume we optimize against to get a new design. And that's what we have on the top right here. Then we're going to assume that we send these results for experimental validation, which again, the challenge is that this can take time, and hope that we get back something that has an overall distribution that performs better than the original distribution. And the thing we want to do is predict how the distribution of these measurements before we get the result back. So the naive way to do this would be we could basically just take point estimates out of our ensemble models, if we have them, or just regular models, to estimate the predicted distribution of our library. But this has a number of problems, which is what we're going to be talking about today. And so our forecasting approach uses a number of techniques and improvements to come up with a more accurate estimate. Okay, so what are the problems with this naive approach as I described it? The first is that empirically, we observe that this tends to lead to a unimodal assumption. So in lots of our internal experiments and in other places, you can see that if you train a model on some sort of biological sequence measurements, then optimize it and use its predictions to estimate how well the library will perform, most of the sequences will be predicted to do well and sort of be around this central mode that you can see pictured here. And in practice, this varies from what we observe. And there are sort of two reasons for this. One is because when you're doing high throughput experiments, you tend to have some amount of dropout where sequences that may actually be functional will disappear at various steps, sort of often randomly. And then second, there often are broken sequences that you just didn't predict correctly. The second problem with this is there's an unaccounted for distribution shift, both in covariate and label space. So on the covariate side, when you design a machine-guided library, you're often moving edit distance further away from some reference point or just further from the training set. And then you also may be inducing more subtle shifts based on what the model thinks is going to be a good performing sequence. And then on the label side, we just want to design better things. And so hopefully, if you do things right, there's this rightward shift of the label distribution. Finally, there's this problem that if you just take the aggregate point estimates and use them to construct a distribution, they're not going to capture population level rare events. Instead, they'll tend to trail off. You can see sort of this cliff here. And this is because while on an individual basis, any given sequence's probability of being like a better than we expect hit is very low, on an aggregate basis across the library, we see that there tends to be a reasonably high frequency of these right tail hits. Okay, so now how do we address each of these issues? For the unimodal assumption, we have a Gaussian mixture model per sequence. For the unaccounted for distribution shift, we use non-parametric calibration methods to improve our predictions. And then for the point estimates not capturing rare events issue, we use the fact that we now have a distribution per sequence to run simulations to compute a library level posterior. So now we're going to walk through each of these in a little more detail. With the point estimate approach, we assume we started out with just a mean parameter basically to construct this blue distribution. And now for the mixture model, we're moving to a world where we are going to infer, and we talk about how we can infer these in the paper, a probability which determines whether you're in this like left non-functional mode or this right functional mode. And then for each of these, you have mean and standard deviation parameters. And together, this gives us, as I mentioned already, a distribution for each sequence's labels. Okay, so for the unaccounted for distribution shift, as I mentioned already, we use non-parametric calibration. Specifically, we use isotonic regression as a function of properties of the sequence to deal with the covariate shift. And unfortunately, I won't have time to talk about these in detail, but we use various methods for dealing directly with the label shift. And again, you can look at the paper if you want to learn more about these or follow up with us. And then finally, for the rare events issue, because we now have this inferred distribution for each sequence, we can run simulations from the library level posterior where we draw one sample per sequence for each library. And then we can repeatedly draw entire libraries. And this allows us to compute the frequency for very rare events, which we couldn't do with the naive approach. Okay, so now I'm going to talk through some results. In the paper, we cover 4 experimental settings, all based on publicly available data sets. Today, I'm going to focus on the AAV and RNA landscape data sets, but again, you can refer to the paper for results in these other ones. So AAV is a small virus used for gene therapy. This is the virus we focus on engineering at Dino, so we're very interested in it and really focused on it. The measurement we're going to be talking about here is something called packaging. So it's basically how well this virus assembles into its structure and then also encapsulates its genome inside it. And for this experiment, what we're going to be looking at forecasts made based on having a training set of random mutants, which are then used to forecast the performance of a design set of sequences. And all of these are, again, based on a public data set that was shared using specifically AAV2 data. And so in this plot on the left here, what we're looking at is some summary statistics getting at the forecast performance. So what we have here on the x-axis is normalized packaging rate. So of the test set. So 0 would be no packaging, 1 would be the best in the test set. And then the different colors denote different data sets. So green is the ground truth. It's the thing we're trying to forecast. Orange is the naive estimate. So this is coming from, again, the naive point estimate method. And blue is the forecast from our method. And then the different shapes denote different statistics of these data sets. So high level, what you see here is that the forecast is getting a lot closer to the true measurements. Here it overestimates them a little bit, but it's just much closer to the actual measurements for all of these statistics. And this may feel a little qualitative for some of you. So we can also look at another metric we have here, which is the Kolmogorov-Smirnov score for different subsets of the distribution above different percentiles. The Kolmogorov-Smirnov score is a measure of distributional fit where lower is better. And so here you can see we're comparing the forecast against the point estimate for different subsets of the data set. And overall, what you see here is that the forecast tends to perform better than the point estimate. They do converge at the tail here, but for a large fraction of the distribution, these subsets, it's doing better. And then finally, we have a third plot, which I think can be a bit more interpretable. And this is looking at counts above the threshold. So the idea here is you have this library, you have a range of packaging efficiencies. These are out now on the unnormalized scale. And you can say for each of these thresholds, how many variants have this measurement or more. And then for the point estimate, you can say what's the estimated count or the predicted count. And then the cool thing is that for the forecast, because we can actually do simulations and get a posterior, we can come up with confidence intervals. And so that's what this is showing here. So the blue is the point estimates. The green is the range of these confidence intervals. And then the X is the true count. And the high level story here is that, as you might expect from these first 2 plots, the confidence intervals have pretty good coverage. They capture the true counts in all cases. They do definitely have like broader ranges for these rightmost points, but relative to the point estimates, you can see this third problem we talked about where the point estimates tend to bottom out quickly because they're not capturing these rare events. Now we're going to talk a little bit about the RNA side. So I'm going to go a little bit faster just to make sure keeping on time. We have this very noisy plot here. So the nice thing about these are in silico RNA binding landscapes. And so what we're looking at here is how the forecast performs on many different local starting seeds. And basically the high level thing we see here is a few things. So first we see that the model, while forecasting is much less accurate here than on the AAV data sets, we are pretty unbiased for these cases where we miss. Another thing you can see here is that, so these middle rows is where I'm just telling you our models are really accurate. And so you can see that here, the point estimates tend to do pretty well, and then the forecast just gets you the rest of the way. And then finally, for this last point I'll make is you can see that even when the forecast is really inaccurate, we tend to capture like the stretch between the mean and the top score better. Okay, so similar story on the right here. The forecast clearly does worse than in the AV. I don't want to like sugarcoat that, but it's still performing better than the point estimates. And so with my 1 minute, I just want to run through some takeaways. The first takeaway here is that our approach, we think it's pretty general. It can be used on any machine-guided library design for which we have regression models. It's not just AAV. And another aspect of this is you can swap in different pieces to this approach. So we talked about using a GMM, which makes sense for a lot of these high throughput settings, but I think you could imagine swapping some other distributional estimator there. Second, we think this work solves an important problem, machine-guided design, where we have these long feedback loops. And third, we hope that we've sort of set up this framework and defined an expansive version of this problem that will inspire further work in this field. And finally, again, if you're interested, you can follow up with us or check out our full paper. Okay, I think 7 seconds remaining. Very good. Thank you, everyone. And this is just a picture of all of us at Dino, and I should have our hiring. Okay, thanks.
Okay, great. Thank you, Stephen. We don't have